Example 3, find the point on the parabola y squared equals 2x that is closest to the point 1, 4. And what I'd like us to do here first is actually sketch that parabola y squared equals 2x. Because I think a lot of us maybe haven't graphed something before quite like this. So here's our x and our y axes sketched in here. And we have our curve y squared equals 2x. You have two options here in terms of graphing it. You could solve this for y and you'd get, y equals plus or minus the square root of 2x. And you could graph both of those curves, y equals the square root of 2x and y equals minus the square root of 2x, and it would give you your parabola. Or, as an alternative, you can actually solve this for x instead. We could say x equals 1/2 y squared. And rather than plugging in x values, we could plug in y values. For instance, if you were to say let y equals 0, then x would be equal to 0, right? So you could go plot 0, 0. Let's try and plug in y equals 1 now. Let's try that. So if y equals 1, then x is going to be equal to 1/2 times 1 squared, which is 1/2. So I'll go to x equals 1/2 and up to y equals 1. And that looks about right. And we could also actually say the same thing about y equals minus 1. X equals 1/2 times minus 1 squared is equal to 1/2. So I'll go to x equals 1/2 and down to y equals minus 1. So there's another point. Okay. Let's try another one. Let's try y equals 2. So we do that, we get x equals 1/2 times 2 squared, which is equal to 2. So we're going to go, equal to 2. So we're going to go to x equals 2, y equals 2. And if we were to look at y equals minus 2 on the other side, we have x equals 1/2 times minus 2 squared, which is also equal to 2. So we'd come down here, and we'd go down to minus 2. And if we were to connect the dots here, we'd see that we have a parabola. And so in this question, what we're really trying to minimize is this distance between this point and the curve y squared equals 2x. So let's go ahead and move back over here, and we are going to set that up. So the first thing that we need to know is, how do we write the distance of just some random point to the point 1, 4? Well, that would look like, let me actually write some words here first. The distance between x, y and 1, 4 is given by d equals the square root of x minus 1. So this is just subtracting the two x values, or finding the distance between the two x values and squaring them, plus the difference of the two y values and then squaring them. So this is the function that we want to minimize. We want to find the point that's closest to 1, 4, but that's also on the curve y equals, or y squared equals 2x. Okay. We haven't incorporated the y squared equals 2x in here yet. So this is our objective function, but we still need to reduce it by a variable. Objective function. Well, our constraint, let's see what that is. Our constraint is that we are on the curve y squared equals 2x, or equivalently x is equal to 1/2 y squared. And so all we're going to do here is we're going to replace this x with 1/2 y squared. So this is going to leave us with d is equal to the square root of 1/2 y squared minus 1 squared plus y minus 4 squared. We are in Desmos now, and I've rewritten our objective function a little bit differently here. It was actually 1/2 y squared minus 1 in here. Let me highlight this. This x squared in here was a y squared, and this x right here was also a y. I chose to write it this way so we could imagine its graph a little bit more easily. Okay. And is what we were trying to do with this function was find the smallest value on it. Okay. And you can actually already see the answer that we're going to end up getting here later on, except for it won't be x equals 2, it'll be y equals 2. Okay. But we didn't need to look at this graph. We're looking at it for a different reason. Okay. We're looking at it because there's actually something really neat that we can do on a problem like this. So this number here, the square root of all this stuff, well, it's going to be some positive number, right? We're talking about a distance here. And so if you were to take any of those distances and square them, they'll still be positive. And so the idea is that this function g, it's actually going to have this minimum at x equals 2, but so will it's the square of it. Okay. And let me actually write it in the way that I mean. So if we were to square g, we wouldn't have that square root there anymore, right? Okay. And let me graph this. And you can actually see this thing does have a minimum at the exact same spot that this one does. Okay. And by the same spot here, I mean, in this case, the x values are the same, right? These both happen at x equals 2. Okay. Again, on our original example, it'll be y equals 2, but this is the idea. These things both have a minimum at the same point. Okay. So we're going to go back, and rather than looking at our objective function, we're going to look at our objective function squared. Okay. And the reason we want to do that is taking the derivative of the one I just highlighted here is a lot harder than it is to take the derivative of this one.